Welcome back. This is Mr. Hassan's Maths channel, and I'm now going to go through question number 6 from the P4 International A-Level Edexcel Specimen paper. And this question here is about vectors. Relative to a fixed origin O, the points A and B have position vectors 9, 5, 12 and 13, minus 3, 4. Now they didn't have to say O to A equals, because position vector means from O to that point. So the position vector of A means O to A. So they didn't actually have to tell us that. Okay, they could have just mentioned this without writing O to A and O to B, but they kindly told us. It says the line L1 has equation R equals O to A plus lambda 2, 1, 3. That means this is the position vector of a point on the line. That means this line goes to the point A. And this is the direction of the line, 2, 1, 3. So you have the position vector plus a scalar quantity times the direction. So we could rewrite this as, just write what O to A is, just 9, 5 and 12 plus lambda times the direction, which is 2, 1, 3. So this is line 1 vector equation, and line 2 we can write O to B as 13 minus 3 and 4 plus mu, the scalar mu, times 10 minus 5 and 1. Okay, so that's the equation of line 1. And equation of line 2, it says where lambda and mu are scalar parameters, show that line L1 and line L1 and L2 intersect at the point X and find the coordinates of X. Okay, so these two lines will intersect at the point X, and we've got to find the coordinates of X. Now, when two lines intersect, okay, there will be a value of lambda and a value of mu, which will give you exactly the same coordinate. So if I put a value of lambda in here, it's going to give me, a vector which represents the position of a point. Okay, because this is like, if this is O, this is A, that's the vector O to A. That takes me, this part takes me to this particular point here, A. And then I have a line going in this direction, and depending on what the value of lambda is, it's going to take me from there to somewhere on this line. Okay, so if I can find a value of lambda and mu which takes us to the same point, then these two lines will definitely intersect, because then this line, say this is B, and if they intersect, there will be a value of lambda and mu which will take us to the same point. Okay, so the way to do this is to equate these two equations to each other, make them equal to each other. So we can say that there's a value of lambda and a value of mu for which these two will be the same. They'll give you the same thing. So 9, 5, 12 and 2, 1, 3. So 9, 5, 12 plus lambda times 2, 1, 3. Let's just make sure of that. 9, 5, 12 and 2, 1, 3, that's right. And you've got 13 minus 3, 4 and 10 minus 5, 1. That's going to be equal to, I said 13 minus 3, 4, 13 minus 3 and 4 plus mu times, and you got 10 minus 5 and 1. So, okay, so if they intersect, then there's definitely going to be a value of lambda and mu which will take us to this particular point where they're equal to each other. Okay, so now what I need to do is I can form from here 3 equations. One equation I can form by looking at the I components. So I can say 9 plus 2 lambda must be the same thing as 13 plus 10 lambda, 13 plus 10 mu, sorry. And then I've got 5 plus lambda is the same thing as minus 3 minus 5 mu, and 12 plus 3 lambda is the same thing as 4 plus mu. 4 plus mu. Okay, 4 plus mu. Okay, so I have equation 1, equation 2 and equation 3. So if I can find what lambda and mu are from one pair of equations and prove that those values of lambda and mu satisfy the third equation, then I will have proved that these two lines intersect, and then I can find where they intersect. So let's take equation 1 and 2 and try to solve this equation simultaneously. So you could do this in a number of ways. You could use some sort of substitution, or you could use simultaneous equations. Let's use simultaneous equations. Let's multiply equation 2, multiply it by 2. In that case, you're going to get 10 plus 2 lambda equals minus 6 minus 10 lambda. And let's write equation 1 down underneath it, which is 9 plus 2 lambda equals 13 plus 10. This is a mu here, sorry. This is a mu plus 10 mu. Okay, so if I take these two equations and I add them together, if I have these two equations and add them together now, I'm going to have 19 plus 4 lambda equals minus 6 plus 13, which is that's going to be 13 minus 6, which is 7, plus 0. This becomes 0, which we wanted to eliminate, so that's why I added them together. So I can say 4 lambda is equal to 7 minus 19, which is minus 12, so lambda is equal to negative 3. And if lambda is equal to negative 3, we can find what mu is. For example, we can take this first equation here. Take the second equation here. We have 5 plus minus 3 equals minus 3 minus 5 mu. Bring the mu on this side, so you're going to have 5 mu equals minus 3, and this is 5 minus 3, which is 2, so minus 3 minus 2, so you're going to have 5 mu equals minus 5, so mu equals minus 1. So I now lambda equals minus 3 and mu equals minus 1. So let's now see if they satisfy equation 3. So now we have to check equation 3. Okay, so we're going to say 12 plus 3 times minus 3 equals 4 plus minus 1. So this gives you 12 minus 9. 12 minus 9 equals 4 minus 1. So 3 equals 3. Yes. Okay, lambda equals minus 3 and mu equals minus 1 are, satisfy both equations, both sides of the equation. So basically, we know that for sure they intersect. Okay, as all three equations are satisfied by lambda equals minus 3 and mu equals minus 1, therefore they intersect. They intersect. Okay, now to find the point where they intersect, we can substitute lambda equals minus 3 or mu equals minus 1 into either of the two equations. Let's use mu equals minus 1 because it seems easier to substitute minus 1. So if you put u equals minus 1 into the equation line 2, okay, mu equals minus 1 into equation line 2, we're going to have r, the position vector of x, will be given by 13 minus 3, 4. 13 minus 3, 4 plus, so you're going to have minus 1 times, because mu is equal to minus 1, so the lambda becomes, the mu becomes minus 1, 10 minus 5 and 1. 10 minus 5 and 1. Is that right? 10, 5, yeah, that's right. So you're going to have here 13 minus 10, which is 3, minus 3 plus 5, which is 2, and 4 minus 1, which is 3. So you can say the coordinates of x are 3, 2, 3. They want it in coordinate form in the end because they say find the coordinates of the point x. Okay, so we've shown that they intersect, and we've also found the point where they intersect. Now, if you wanted to make sure that you were correct, you could have put lambda equals minus 3 into this equation here. If you put lambda equals minus 3 in here, you're going to have 9, 5, and 12. And you're going to have minus 3 times 2, 1, 3, which gives you, let me just make that a bit neater. If you were to try lambda equals minus 3, as I said, you have 9, 5, and 12, minus 3 times 2, 1, and 3. And that would give you 9 minus 6, which is 3, 5 minus 3, which is 2, and 12 minus 9, which is 3, gives you exactly the same point. So we know for sure, just in case you wanted to check, that we have got the right answer. When lambda is minus 3, this line is going to be at this point. This will be the position vector of this point. And when lambda is -1, then this line 2 is going to be exactly the same point, 3, 2, 3. Therefore, they intersect at that point. Okay, so that's question number 6a. Okay, now for 6b. 6b says find the coordinates of the point P such that XAPB is a parallelogram. So if you remember, we had line 1 and line 2. Let's say that's line 1 and line 2. Okay. We know that they intersect at X, and we know that line 1 goes through A, and line 2 goes through B. Okay, they pass through A and B. Okay, and it says find the coordinates of the point P such that XAPB is a parallelogram. Okay, let me just draw the B over here so I've got more space underneath. So let me draw it like this. Let's say this is A and this is B. Okay, so XAPB. I just want space. I want to have the space down here, that's all. So XAPB. So basically, if it's a parallelogram, then you're going to have a line that's going to be going parallel to that line. Okay, so let me just draw a line like this and just bring it down. It's parallel to that line. Okay, and it's going to be the same length as, in fact, I'll just do it like this. Be the same length as XB. So make it the same length as XB and over here. So it's going to be parallel to it and the same length as it. Okay, so that's going to be P. Okay, so it's parallel to XB. That's AXBP. This is now a parallelogram. Okay, so these should be parallel to each other. Let me just draw that a bit better. Okay, so these two lines are parallel to each other. Okay, there we are. Okay, that's fine. So that's B, that's P, that's A, that's X. Okay, so this line is parallel to that line, and this line is parallel to that line, and we have a parallelogram. Okay, so it says find the coordinates of the point P. So we need to find the coordinates of point P given such that XAPB is a parallelogram. So let's say this is a point O over, let's say over here. Say that's the origin. Okay, we want to find the coordinates of P. So basically, what we want to find is, let me do it so it's clearer. Let me put the point O somewhere over here where it's easy to see. Okay, so now the coordinates of the point P. So we need to find O to P. That's what we need to find. Okay, what we need is O to P. Okay, now what do we have is we have X to B. Well, we can find X to B. First of all, let's say O to P. We need to find O to P. Now, O to P, you could say, is like O to A plus A to P. So O to P is the same as O to P is like O to A plus A to P. Now, O to A I know. O to A I know is the position vector of A, which was given to us as 9, 5, 12. Okay, so this is 9, 5, 12. Now what I need to find is the vector from A to P. Okay, I need to find what A to P. Now A to P must be the same exact vector as X to B. Why is it the same vector as X to B? Well, because this is the side which is opposite to A to P in a parallelogram, so they're the same direction, they're parallel, and they are the same length. So they will be described by the same vector. So I need to find what X to B is. Now X to B, if you think about it, is going to be like this. Let me just put this in a dotted line so it's a bit clearer. So you have O to X and you have O to B. Okay, we want to find X to B. So X to B is like going from X to O and then from O to B. So X to O is like minus OX. So what we can say is it's like OB minus OX. Now O to B we already know from the first part of the question. O to B is 13 minus 3 and 4. So we have 13 minus 3 and 4. 13 minus 3 and 4. Minus O to x we found as 3, 2, 3. If we just remember that correctly, it was 3, 2, 3. That was O to x, the position vector of the point x where they intersect. Okay, so this is going to give me 13 minus 3, which is 10, minus 3 minus 2, which is minus 5, and 4 minus 3, which is 1. So this is the vector x to b, which is the same as a to p. That's a to p. So as we said earlier, O to P is O to A plus A to P. O to P is O to A. O to P is O to A plus A to P. And I have all of those things now. I know what O to A is. Okay, that's, as I said, 9, 5, 12. That's given in the first part of the question. Plus A to P, we just found it, which is 10 minus 5 and 1. So I end up with 10 plus 9, which is 19. 5 minus 5, which is 0. And 12 plus 1, which is 13. Okay, let's just make sure of that. Let's just make sure that's O to A 9, 5, 12. That's right. And here we have O to B, which is 13. O to B, O to B. 13 minus 3, 4. Yep, okay, so that's 13 minus 3, 10. Minus 3 minus 2, which is minus 5. And 4 minus 3, which is 1. And then I have to add these together. So 9 plus 10. Yeah, okay, so there's the answer. So we can say that they asked us to find the coordinates of P. Therefore, P, the coordinates of P are 19, 0, and 13. And there's the answer to question part B. Now for part C, it says show that XAPB is a rhombus. Okay, so XAPB, we have to show that it's a rhombus. Now, what do we know about the rhombus? Okay, now this is something which you have to remember, some of your properties of the special quadrilaterals, which you should have learnt in your IGCSE course. Okay, so some of the properties of a rhombus, basically all the sides are the same length. Okay, that's one thing we know, and the other thing we know is that the opposite angles are equal. But one of the very important properties of a rhombus is that the diagonals intersect at right angles. The diagonals of a rhombus intersect at right angles. So that's what will help us here. So that means AB and XP should intersect at right angles. Okay, so what we need to do here is we need to show that in a rhombus, we have to use this fact. If it's a rhombus, then this, for sure this will be true. The diagonals intersect at right angles. Okay, so therefore we have to prove that they intersect at right angles. So that means basically AB and XP must be perpendicular. Therefore, the vector from A to B is perpendicular to the vector from X to P. Okay, so we have to prove that. Now we can use the dot product to prove that. If the dot product of A to B and X to P is equal to 0, then they definitely intersect. They are perpendicular. Therefore, the diagonals intersect at right angles. And if that's true, then it's definitely a rhombus or a square. And a rhombus is like, or you could say a square is like a special type of rhombus. So it will still be counted as a rhombus. Okay, so there's no problem there. So now, let's just, so a square is like a rhombus with angles of 90 degrees, that's all. So you could class a square as a type of rhombus. So anyway, so we got to find the vector from A to B and the vector from X to P. Okay, do we have X to P or no? We don't have X to P. So the vector from A to B is basically A to O plus O to B. So it's going to be, A to B is going to be basically OB minus OA. So the vector from A to B is going to be OB minus OA. Okay, and the vector from X to P is going to be basically similarly kind of, if you think about it in the same way, from X to P is going to be from X to O and then from O to P. x to p will be x to o, then o to p. Okay, so that's going to be basically OP minus OX. OP minus OX. O to P minus O to X. Okay, O to B minus O to A. Now O to B minus O to A, so you have the position vectors you're looking for. 13 minus 3, 4, and 9, 5, 12. 13 minus 3, 4, 9, 5, 12. So you have 13 minus 3, 4, minus 9, 5, and 12. Okay, and from O to P minus O to X, so we need O to P, which we already found. So that's 19, 0, 13. Minus O to X, which was 3, 2, 3. Okay, so this is 13 minus 4, 9, which is 4. Minus 3 minus 5, which is minus 8. And 4 minus 12, which is minus 8 as well. That's a vector from A to B. And the vector from X to P is going to be 19 minus 3, which is 16. 0 minus 2, which is minus 2. And 13 minus 3, which is 10. So we can do the dot product of A to B times X to P is going to be given by 4 minus 8 minus 8 dot product with 16 minus 2 and 10. So you have 4 times 16, which is 64, and then you're going to have plus minus 8 times minus 2, which is minus 16, and you're going to have minus 8, you're going to have, that's plus 16, sorry, because minus 8 times minus 2 is plus 16, and you're going to have plus minus 8 times 10, which is minus 80. Okay, so you have 64 plus 16, which is going to be 74 plus 6, which is 80 minus 80, which is 0. So you can say basically so you can say that therefore as the dot product of A to B and X to P is equal to 0, they are, or you can say as, let's write it more neater than this, it should really go on the next page. I'm just going to do it over here. So we can say as the dot product of A to B and X to P is equal to 0, therefore A to B is perpendicular to X to P. And as the diagonals of XAPB are perpendicular, therefore XAPB is a rhombus. Okay, so we know for sure it's a rhombus. It could also be a square, because that's also true for squares. However, a square is like a special type of rhombus. It's like a rhombus which have angles of 90 degrees. That's all. So it still could be classed as a rhombus technically. Okay, so that's for sure it's a rhombus, because whenever you have the diagonals of a parallelogram intersecting at right angles, it's definitely a rhombus. The only other shape where the diagonals, one of the other shapes where they intersect at right angles is called a kite, but that's not a parallelogram because the sides aren't parallel to each other. So we know it's a parallelogram. We know the diagonals intersect at right angles. Any parallelogram where the diagonals intersect at right angles, for sure, is going to be a rhombus or a square. And as a square is a special type of rhombus, okay, then it's for sure we can class it as a rhombus. Then that's part C done. Now we're going to go on to part D. Okay, so for part D it says prove by contradiction that XAPB is not a square. Okay, it's not a square. Now it says prove by contradiction. Okay, so that means basically when we do proof by contradiction, now this is a new part of the syllabus here, but they've kind of intertwined it with this topic. But proof by contradiction is when you first assume the opposite. So we say, okay, let's assume, so you have to write something down in this type of question. Let's assume that XAPB is a square. Okay, we have to assume it. Okay, so if XAPB is a square, then the sides are perpendicular. The sides are perpendicular to each other. Not the diagonals, the sides. Okay, so let's go back to the diagram here. Let me just take a little snapshot of it. Okay, so here we have a snapshot of the diagram of this. So far it's a rhombus. We've got to prove it's not a square. As I said, if it's a square, so we assumed that it is a square. If XAPB is a square, then the sides are perpendicular. So that means, for example, XA is perpendicular to AP, for example, right? So if we can find what XA is and AP is, and we can multiply them together, so therefore we can say that the dot product of XA and AP has to equal 0. Okay, if it is a square, then this will be true. Okay, so let's find what XA is. I think we already found it. XA. Did I find it already? No, I found XB. If I found XB, and I have to find one of them anyway. So let's just find what XA is. Now x to A, okay, x to A is going to be O to X, X to O minus, so X to O plus O to A. So it's going to be OA minus OX. OA minus OX. Did I find it anywhere? No, OA minus OX. Okay, let's find what that is first. So we're going to have OA minus OX, O to A minus O to X. And A to P, I'm sure I found A to P somewhere. A to P, yes, it was the same as X to B. A to P was 10 minus 5 and 1. 10 minus 5 and 1. So I know A to P is 10 minus 5 and 1. So let's find what X to A is. So O to A, if we go back here, O to A is 9, 5, 12. 9, 5, 12. 9, 5, 12. And O to X was 3, 2, 3. So we have 9 minus 3, which is 6. 5 minus 2, which is 3. 12 minus 3, which is 9. Okay, so we can say that now the dot product of X to A times A to P is going to be 6, 3, 9 multiplied by 10 minus 5, 1, which gives you 60 minus 15 plus 9, which is 45 plus 9. That's 45 plus 9, that's right, yeah, which is 54, of course. Therefore, as XA dot product with AP is not equal to 0, therefore it's a contradiction. It's a contradiction because we assume that it is going to be equal to 0. Therefore, XAPB is not a square. Okay, so that's how you can show this contradiction. Okay, so you first of all, when you prove by contradiction, you first assume the opposite. So first of all, I'm going to assume it is a square, and then if it's a square, then for sure the sides must be perpendicular to each other. And as I've shown that, you know, XA and AP are not perpendicular, therefore it's not a square. Okay, so that's how you can prove by contradiction, and that's the end of question number 6 about vectors, and also a bit about proofs there at the end. And yeah, so that's the end of that question. Thank you for watching. Other questions from this paper will be found in the playlist that should appear on in this section over here, and over here should appear a question to do with, or the playlist with vectors from P4. You can subscribe to my channel over here, and on the top here you'll find a link to another playlist from P4 paper. Thank you for watching, and see you soon.